One thing that's nice about the SI system is since it's based on the number 10, we have prefixes we can use that scale the basic units up or down depending on the size that we need. There are lots of these prefixes. You can look in on Wikipedia or in some reference book and find many, many prefixes. These are the ones that turn out to be most often used in chemistry, at least in our class. Kilo is a prefix that has the symbol small k, and its value is 10 to the third, or 1,000 of something. For example, there are 1,000 grams in 1 kilogram. Centi is a number that scales something down. Centi is abbreviated small c. It's 10 to the negative 2, or 1/100th of something. For example, there are 100 centimeters in 1 meter, because a centimeter is 100th. Milli is abbreviated small m. That's 10 to the negative third, or 1/1000th of something. So there are 1,000 milliliters, for example, in 1 liter. Micro is abbreviated with the Greek letter mu, because m has already been taken, you can see. This is 1/1,000,000th, or 10 to the negative sixth of something. So that means there are 10 to the sixth, or 1,000,000 micrograms in 1 gram, for instance. And then there's a really tiny one, nano, abbreviated small n. That's 1,000,000th, 10 to the negative ninth of something. So 10 to the ninth nanometers are in 1 meter. Nanometer is very small. We would use it for measuring things like how far it is across an atom or a molecule. Converting units can be done by a couple of methods. One of them is by using proportions. You can use proportions simply because we know that, first of all, the scales are linear. If you want to convert grams and kilograms, well, there's the same number of grams in every kilogram. It's 1,000 grams every time. So 1,000 grams, 1 kilogram. 2,000 grams, 2 kilograms, and so on. It's linear. Second of all, if you don't have any mass at all, well, it's 0 grams and 0 kilograms. So that line goes through the origin. It goes through 0, 0. Here's what that means. I can use a simple proportion and cross-multiply to solve these kinds of problems. Like this one. How many grams are 2.2 kilograms? I can set this up as a proportion. I know that 1,000 grams is 1 kilogram. So therefore, if I put 2.2 kilograms in the denominator on the right-hand side so that the units match, my unknown here I can solve by cross-multiplication. 2.2 times 1,000 is going to give me x. When I divide by 1, 2,200. Two significant figures. That's the number of grams. There's another tool that we can use here that's very powerful, extremely useful. One of the most important things you learn in science classes is this thing called dimensional analysis. It's extremely good at converting units, but you can do other things with it too, as we're going to see. It's built on two principles. The first one is dividing anything by itself or by an equivalent to itself results in the number 1. For example, I know that 5 divided by 5 is 1. I also know that 2 plus 3 divided by 5 is 1. I also know that 4 plus 1 divided by 5 is 1, because 4 plus 1 is 5. So that means also that 2 plus 3 divided by 4 plus 1 is also 1. No matter what form of 5 I have in the top and the bottom, as long as I have 5 in the top and the bottom, it's 1. The second principle is that multiplying anything by 1 never ever changes its value. So let's say I started out with 5 and I multiply by 1. I got 5. If I take 5 and I multiply by 1 times 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 1 till I get really, really tired of it, I still have 5. Now, if you creatively select values of 1 to multiply by, you will always keep the same value, but you may change the unit. And that's where this becomes really handy. For example, going back to that last problem, what is 2.2 kilograms in grams? I can set this up this way. 2.2 kilograms is my starting unit. And then sometimes I just draw a line here to represent the fact that I'm going to be doing some unit conversion, some dimensional analysis. And I'll put my target unit over here. It's asking for this in grams, so G is where I want to end up. Now I ask myself, how can I multiply this by 1 in such a way that I end up with grams instead of kilograms? Here's how it works. I know 1,000 grams equals a kilogram. So if I take 1,000 grams and put it up here, and 1 kilogram and put it down here, I've just multiplied by 1, because 1,000 grams is 1 kilogram. So I haven't changed the size of this weight. What I have done is allow myself to cancel out kilograms, because I have kilograms on top and bottom. That unit now disappears. The only unit left is grams. Well, 1,000 times 2.2 is going to give me 2,200, just like it did when I did it by proportion. You can extend this technique for more than one step if you need to. For example, if I wanted to know what is 410 nanometers in centimeters, I might set it up this way. 410 nanometers is my starting point. Centimeters is my ending point. How am I going to get there? Well, here's one way. I know that there are 1 billion, or 10 to the 9th, nanometers in 1 meter. So multiplying by the ratio that I just wrote there doesn't change the size of this length. But it does change the unit, because now nanometers are going to cancel. Well, I don't want meters. That's what I'm ending up with here. I want centimeters. So I'll do it again. I know that 1 meter is the same thing as 100 centimeters. What that does for me is doesn't change the size of the length, because 100 centimeters and 1 meter are the same thing. Dividing something by its equivalent is just 1. So multiplying by 1 again doesn't change the size. But it does change the unit, because now meters also cancel out. The only unit I have left is centimeters. Since my unit is right, I know that my number is going to be right. Now I calculate 410 times 100 divided by 10 to the 9th. This ends up giving me 4.10 times 10 to the 5th centimeters. I can use this to convert from one unit system to the other, as long as I know a conversion factor. Like in this problem, how far is 4 miles in centimeters? My starting point for this calculation is 4.00 miles. My ending point is going to be somewhere over here, centimeters. How do I get there? Well, I know one thing. This is the one fact that I can always remember. 2.54 centimeters is equal to 1 inch. That's a useful thing to know. Might want to sketch that in your notes there. That's how I can get from the English system into the SI system. But I don't have inches here, I have miles. I also know that 5,280 feet is the same thing as 1 mile. And I know how many inches are in a foot, so I can get to centimeters from there. Miles are now gone. I haven't changed the length, because I've just multiplied by 1. Well, there are 12 inches in a foot, so if I put 1 foot down here and 12 inches up here, I now get rid of feet. But I haven't changed the length, because I just multiplied by 1, because 12 inches in a foot are the same thing. Now I can convert. 1 inch is 2.54 centimeters. Well, I haven't changed the length again, because I've only multiplied by 1. But because I was selective in what I meant by 1, inches I can now cancel out too. The only unit left now is centimeters. So I'm ready to calculate and get my answer. The answer comes out to 644,000 centimeters. Now, why did I choose to write that number that way? Because my calculator gave me a different answer with more digits, more significant figures. Here's why. In 4.00, which is my starting measurement, my precision reports that I only have 3 significant figures. 5280 has 3 significant figures, but that's really not true either, because this is definition. 5,280 feet is exactly a mile. That's an exact number. 12 inches is exactly a foot. That's an exact number. And this 2.54 centimeters is an inch. That's also an exact number. That's the definition of what an inch is now that we have the SI system. So with those 3 as exact, the only thing that really matters is how many significant figures are in 4.00, and that's 3. So I rounded my answer off to 644,000, 3 significant figures. This is also useful for problems that have nothing to do with unit conversion. For example, we've been using proportions to go between atoms and moles. We can do that with dimensional analysis too. Watch this. Starting out with 0.350 moles, I want to know how many atoms that is. Well, here's a factor. I know that 1 mole is 6.022 times 10 to the 23rd atoms. That's Avogadro's number. Since 6.022 times 10 to the 23rd atoms is 1 mole, I'm multiplying by 1. But when I multiply by 1 this way, moles are going to drop out and the unit changes to atoms. My answer to 3 significant figures is 2.11 times 10 to the 23rd atoms. I want to do one more example for you just to show you a potential error that can happen when you use your calculator to do dimensional analysis problems. This question is asking, what is the length of a second in years? Well, 1 second is our starting point, and years is our ending point. This is all about time, and we're pretty familiar with some time conversion factors. I can change seconds into minutes pretty easily because I know that there are 60 seconds in 1 minute. So multiplying by that factor gives me minutes. I also know there are 60 minutes in 1 hour. So multiplying by this factor changes me to hours. I know there are 24 hours in 1 day. So that changes me to days by multiplying by that factor. And I know that there are 365 days in a year. It's actually 365 and a fourth, but we'll round. So days now cancel. So I have the unit that I need, years. Now I just need to do my calculation. Now watch what happens. If I take 1, divide by 60 times 60 times 24 times 365, which it looks like I'm supposed to do here, I will end up with 8.76 times 10 to the third. Well, that's 8,760 years. That's clearly much longer than a second. So something went wrong here. And here's what went wrong. The calculator did the order of operations in a way that I didn't want it to. It divided 1 by 60, and then it took that quotient and multiplied by 60, multiplied that by 24, and multiplied that by 365. Here's how I can fix this. I take my 1, I divide by, and then I hit my left parenthesis key. Then I just multiply everything that's in the denominator here. 60 times 60 times 24 times 365. Then I close my parenthesis, use my right parenthesis key, and hit enter. Now I have a much more reasonable answer, a small fraction of a year. That makes sense.